Section 12.2, Differentiation and Integration of Vector-Valued Functions. This section covers basic calculus operations using vector-valued functions. Now what you'll notice, despite what operation we may be doing, is that for the most part we get to treat each component here separately. So whether we're doing limits, derivatives, or integrals, we basically get to treat and work with each of these separately and do the normal operations that we would expect. So looking at our first operation, finding a limit, when doing the limit, as our parameter here approaches a certain value of a vector-valued function, we'll apply that limit to the component here horizontally, and then as well apply it to the limit vertically. And again, the answer is still going to be a vector-valued function in terms of the sum of I and j. So for instance, if we did the limit as t approaches 2 of this vector-valued function, we would just simply do the limit of 4t squared and the limit of sine of t theta. Now, of course, our answer is going to remain component form, but we're still going to do the limit of each one of these separate pieces. So letting t become 2 gives us 4 times 2 squared, which is basically 4 times 4. So that's going to give us 16. And then in the other section, we're going to let t, of course, become 2, making this sine of 2 pi, which is, of course, 0. Let's try another example. We're looking at the limit as t approaches 0 of this vector-valued function. So we're going to let t approach 0 in this horizontal component and then in this vertical component to see what the result's going to be. So looking at 4e raised to the t, as t approaches 0, that just becomes 4 times 1. So this right here, of course, is just going to give us 4 times I. And then the sine of t over t, by theorem, of course, as t goes to 0, approaches 1 as well. So this will just be 1j. Now let's look at finding derivatives. So just like doing limits, when we differentiate a vector-valued function, we'll just separately differentiate each piece, right? The horizontal and vertical components. Now what's important to understand about derivatives, of course, though, is that in addition to just seeing where it belongs, when we talk about like a tangent vector, for instance, it's going to start here at the point on the curve. So when we want to calculate or draw any of these, which we'll do in a later example, what you have to figure out first is where does the original vector take you, and from there are the tangent vectors then sketched. So they come from that point of tangency out. So when you make use a derivative and maybe find a tangent vector, it's actually a two-step process. First, finding where on the curve that vector takes you, and then of course once that's done, then from that point in time you'll draw the tangent vector. So back to derivatives, let's go ahead and just do the first step and find them. So like I said, given this vector-valued function, we're going to individually differentiate each of these pieces. So as far as the notation, we can refer to this as the derivative, because again, we're using function notation for the vector-valued function. So in this case, this works out to be 8t cubed I minus 12t j. And finding the second derivative is, of course, doing the exact same thing. This itself is a vector-valued function, so finding the second derivative is done the same way. In this case, our notation will change, saying this is now our double prime, and this will be 24t squared I minus 12j. Now let's try an example trigonometrically. Now here, we're again in component form, but we also want to pay attention to how this derivative here is done. This is going to be a product rule, whereas this one is just going to be the derivative of sine. So when we talk about r prime of t, okay, in component form, it's going to be the derivative of t times the cosine, so that's just cosine t, minus the derivative of cosine t, which is negative sine, so this would be plus t times sine t, when you multiply that t in there. And then the other part, of course, will be the derivative of negative 2 sine t, which is just negative 2 cosine t. Now for the second derivative, this is where we have to be really careful again to make sure we use the right rule when we make this work. So again, we're going to differentiate the first part. The derivative of cosine t, of course, will be negative sine t. And then we have another product rule. So it'll be the derivative of t, which is 1 times sine of t. And then t times the derivative of sine t, which will be t cosine t. And then, of course, the derivative of negative 2 cosine t will be positive 2 sine t. So for the last operation, since we've already done limits and derivatives, let's look at doing integrals. And again, for the same reason, we just separately do the integral on the horizontal and vertical components. So we'll look at whatever's here and apply that integral. And it is true whether it's definite or indefinite. I just wrote definite here, as well as this piece here. So given our example, if we want to find the integral of this vector-valued function, we're going to individually deal with each of these pieces. So another way of kind of looking at this is we're going to basically do the integral, the definite integral, if you will, from 0 to 1 just on that horizontal piece, right? So this will basically be on the 3 radical t, right, with respect to t, that whole value times I. And then again, we're going to do another definite integral. So again, from 0 to 1. And this time of the 1 plus t plus 1, right, dt. And that will be times our j. Okay, so just to, again, highlight, we're definitely doing each piece separately. So when we look at the antiderivatives here, this is basically going to be, again, the definite integral. The antiderivative is going to be 3/4 t raised to the 4/3. And we're going to evaluate that from 0 to 1. And then we'll add on to, and of course, sorry, times I. And then we'll, of course, add that on to the antiderivative here, which is just going to be the natural log of the absolute value of t plus 1, evaluated from 0 to 1, j. Okay, so if we work this out, obviously plugging in 0 for this will make 0. Plugging in 1 just gives me 3/4. So it'll be 3/4 I plus, and the natural log, obviously, of plugging 1 in is going to be natural log of 2. Plugging in 0 is natural log of 1, which is 0. So this will just be the natural log of 2j. Now let's go back to talking about not only sketching a curve, but also computing a tangent vector. And like we talked about before, we talked about derivatives, this is where we're going to have to figure out where the vector takes us on the curve first, and then from that spot sketching whatever that tangent vector may be. So first off, we have to sketch the curve. Now in this case, we want to go ahead and take a look at it. This is t and t squared plus 2 as far as parametrics. So what I'm going to do is I'm going to take my parametric pieces and rewrite them rectangularly. So in this case, what I can say is that, since x equals t, I can say that y equals t squared or x squared plus 2. So that's going to help me sketch it. So that means that here, at my y-intercept, myself a couple dots. So the curve looks like this. All right, so the next thing, of course, is what we want to do is compute what the tangent vector at 1 is, right? Now, obviously, what we should probably do first is plot where that's going to happen at. So what I need to figure out is where is r of 1? Because I want to know where to draw this tangent vector from. So you have to first figure out at, t equals 1, where are you on the curve? So plugging 1 in is going to give me 1 times I plus, and then 1 squared obviously is going to give me 1 plus 2, which is 3j. Okay, so that means I'm going to go over 1 up 3. So that means it's going to put me right here. Okay, that's where r of 1 is, that spot right there. So the next thing, of course, is let's find the derivative. Because obviously if I'm going to find the tangent vector, I need to know its rate of change. So we're going to calculate the rate here. So in this case, the derivative is going to be the derivative of t times I, so just 1i. And then the derivative of t squared plus 2 is just 2t. So 2tj. And since that's our derivative now, since the point we care about is 1, we're going to plug in and figure out what that vector is going to look like when t is 1. So in this case, plugging 1 in, well, this is just going to be I, and this will be 2j. Okay, so now that I have that, I can actually, from my point of tangency here, I'm going to go over 1 and then kind of up 2 to give me an idea what that vector looks like. So if I do that, if I go over 1 up 2, that takes me right there. And so the tangent vector looks like that. Lastly, let's go ahead and use integration to solve, given the derivative of a vector valued function, for what that's going to be. So obviously, given the derivative of a vector valued function, if we find the antiderivative, that's going to give us obviously a general solution. And then using this particular value that must be true, then we can solve for c and get that particular solution. So the first thing is we have to find the antiderivative. So of course, to find r of t, it means we're going to have to take the integral of our 4e raised to the 2t with respect to t, okay, whatever that's going to be, times I. And then again, we're going to take the general antiderivative here of 3e to the t with respect to t, j. All right, so if I work this out, what's going to happen is here, obviously, I'm going to get 2e raised to the 2t. And there is going to be a plus c, but what I'm going to do is I'm going to take this whole thing, multiply times my I, right? And then what's going to happen is I'm going to move that plus c off to the side, okay? Because you're going to get a plus c with this one, you're going to get a plus c with this one. So I'm just going to antidifferentiate each one, and then generally kind of put those c's together as one general plus c at the end. So this over here, of course, the antiderivative of 3e to the t is just going to be, well, 3e to the t, right? So this is going to be 3e to the t j. And again, because both of them have some unknown constant, we can put those together to be some unknown number. So again, this is our general R of t. So this is our general solution. To find our particular solution, we're going to solve this whole thing, plugging in 0 for t and letting it equal 2i, okay? So that means when we do this, we're going to have 2i equals, and now obviously if we plug this stuff in, we're going to get 2e raised to the 0i plus 3e raised to the 0j plus c. Now, when you simplify this, again, we get 2i. This over here, of course, is just going to be another 2i. This is just a 3j, since, for both of them, e raised to the 0 is 1, plus c. So what that tells me, of course, is that when I subtract, we get 0. I should say when I subtract 2i from both sides. So 3j plus c. So solving for c tells me it's negative 3j. So that means what I'm going to do is I'm going to take this, plug it in right here. Okay, so what we can say now is that for the specific solution satisfying this condition, R of t is going to equal 2e to the 2t times our I plus 3e to the t j, and then minus 3j. Now we can't put these together obviously because they're both j's. So to simplify this, we could go ahead and call this 2e to the 2ti, and then plus, and then parentheses, we can kind of factor out that j. So we'll say 3e to the t minus 3j.